so we've seen that if we make the assumption that every atom has its possible states, and because they're all in some sort of mixture, the two blocks are together, atoms are constantly bumping into one another and exchanging quanta, and the quanta are equally likely to be at any microstate. Remember, all these microstates have the same total energy, and so that any of them are equally likely.
Yep.
You might think this would lead to total anything goes, but in practice, if you add up the total number of possible states to any realistic number of atoms, it's going to drive you very rapidly to thermal equilibrium, everything being at the same temperature. So is this the explanation for the arrow of time? Let's see if it can actually explain what's going on. We should mention that this is actually the definition of entropy. Entropy is defined as a constant designed to fit up with a macroscopic model times the natural log of the number of microstates.
Okay, so we have a model here for entropy and a mathematical way of describing it. So one could imagine as you get more and more microstates, then the entropy rises. This coefficient in front that sort of gives it sort of a unit we're going to be able to compare to energy, for example, later on.
So what it's telling us is that it will tend to move into the situation with the most microstates.
Yes.
It's not because those microstates are any more common than any other microstates, it's because there are so many of them that if you are randomly moving between all the microstates, which is our key assumption here, so that really is random thermal motions, things jiggling backwards and forwards, you are going to end up most likely in a state with a lot of microstates rather than a state with very few microstates, and that's going to be the state with the maximum entropy. So this is the second law of thermodynamics: entropy always goes up and plateaus in the maximum state.
Okay, so let's think about how this helps our arrow of time.
Well, if you take the first situation, the ice melting, it's all pretty straightforward. This is just what we've been talking about. You've got water and ice, and the energy initially was mostly in the water and went into the ice until it equalized out.
Yep.
But how about the second situation, the ball? So a ball sitting on a table and suddenly flings itself upwards. I mean, why does that happen? Well, again, you could look at what happens in the reverse process. Let's say I take a ball and I drop it. So as the ball's flying downwards, the table atoms are going to be randomly moving all over the place. Just
the thermal motion, yep. So the ball hits it.
And the thermal energy in a table is enormous. I do this calculation with my first year physics students. You take a cricket ball and you fast bowl it, you work out the kinetic energy of the world's fastest bowler, compared to the energy gain you get by putting the ball in your pocket for a few minutes so it warms up by 1 degree. And it turns out the energy of warming up a cricket ball by 1 degree in your pocket dwarfs the energy you get from the world's fastest fast bowler. The random energies of the atoms moving around in a ball just sitting on the table are much bigger than anything you can throw it at.
Okay.
So there's actually huge amounts of energy in the table. So anyway, the ball lands on it, and when it lands, it's going to briefly depress the table underneath it, and so you're going to get a very ordered velocity field.
Right, so ordered velocity field, yes?
But then, as it sits there, maybe bounces a couple of times and then comes to a rest, it's going to go back to being random.
Yeah.
That energy you've imparted has ended up as warming up very slightly the table.
Yes. So you've increased the random motions a little bit, but then those motions are random.
Yeah. So you've got to look at all the possible microstates here, which is for each atom it can be moving in any direction. So you've got X, Y, and Z.
Yep.
And because they're moving in any direction, it's all random. In principle, there is a microstate that looks something like this, where while the atoms far away from the ball are moving all over the place, the ones underneath are all pointing upwards.
Right. And
This
so
would be like, let's say that's the Z-axis. It would be all these things have all their quanta in the plus Z direction, as opposed to the X's and Y's.
and this would be a state that would cause the ball to suddenly leave the table and go into your hand very conveniently.
Yes, but of course you can once again count all the possible states and ask what fraction of them would result in a ball jumping out.
Yes.
And so you can do a sort of Venn diagram. So you've got all the possible configurations and the ones that will result in the ball leaping off the table. And that's going to be a very, very, very small fraction of the total.
Yes. Probably a number like 10 to the 1,000 to the 1,000 to the 1,000 or some huge number. Very unlikely.
Yeah, so it's actually exactly the same thing. What we've got is a whole bunch of states, and they're all equally likely. So in fact, of all the microstates, the ones that fling the ball into the air are just as likely as a state over here or a state anywhere else.
Yeah.
It's just there aren't very many states that rely that. There are an awful lot where the ball just sits on the table.
Right.
So just like we're talking about temperature moving between two blocks, the state with all the energy in one block is just as likely as any other state. It's just there aren't very many states like that, whereas an awful lot more states with energy distributed. And by awful lot more, we're not talking about 10 times more. We're talking about 10 to the 100 to the 100 to the 100 to the 100 more. So much so that this basically never happens.
Yes.
Indeed, I've never yet seen a ball fling itself off the
And it's just as well. I think the universe is random enough as is without having the ability to have crazy things happen. Yes.
And the same thing would apply for someone coming out of a swimming pool. In principle, you got when someone dives into the swimming pool, they initially would produce ordered motions of the water. So now you've got to imagine each little bit of water, which way is it moving. But those things break up into eddies and swirls, so-called cosmograph cascade, and ends up just warming up the pool slightly. And in principle, you could be swimming along in a swimming pool suddenly when all the atoms near you happen to have large Z velocities and fling you randomly out to a nearby diving board.
Yep.
But once again, thankfully, the odds of that are extraordinarily unlikely. Okay, so this is kind of making sense. So does this actually apply to everyday environments like messy rooms or civil wars? People often talk about countries falling apart or teenage bedrooms getting messy. This is actually not my teenagers, this is my own study, so I can't blame anyone else for this one. Can we actually apply this whole principle of microstates and counting them at entropy to situations like this?
Well, it's not completely clear. So let's just think what we have here in this room. We have a lot of books, and so let's just only worry about the books at this point. And you will note that the books actually show a fair bit of order. They're all on the shelves. They're not just randomly strewn on the floor.
And if you look closer up, you'd find, for example, that this row here is all the Agatha Christie's, for example.
Okay, I have a row of Agatha Christie's as well, yeah. So if you think about the total number of states, for example, where all the Agatha Christie's are down there, that's a very small number of states compared to all ways the books can be configured.
If you have a number n of books and all the possible ways in which they can be arranged, then maybe we've got some boundaries which might correspond to the edges of the shelves, then we could do the same calculation. And of all the possible states, the vast majority would be chaotic. The fraction of states which you'd go in and say, this is ordered, all the Agatha Christie's are together, all the Jane Austens are together, and so on. That's be a very tiny fraction of the overall total possible number of states. So this kind of works.
Well, it sort of does, except for, of course, this room finds itself in a state of relative order, where you're in a very unusual state. If you think about what you might expect, you wouldn't expect to find all the Agatha Christie's. That's a very improbable act if it was just random.
Yeah, so maybe we've got one part of the whole entropy argument, which is a whole bunch of states, and the chaotic ones vastly outnumber the ordered ones. But the second assumption we need to make this work is that you're equally likely to move between any state. So if, for example, every time I took a book out to read, we just, instead of putting it back on the shelf, just threw it randomly into the room or put it back at random with a blindfold on, and that would maybe approximate the situation that we've talked about in thermodynamics, where the things, or if at night the book pixies came up and randomly moved things around. In that situation, then yes, you'd never have a tidy one. It would rapidly develop to entropy. But that's not really a good approximation in this case.
Yeah, I mean, the best approximation is what happens after you and I are gone, a million years, what this bookshelf looks like in a million years. Then that's going to start looking, I bet you, a bit more random.
Indeed. Okay, so for thermodynamic situations, this all works pretty well. It explains why balls don't jump off tables, it explains why ice cubes don't unmelt out of glass, it explains why you're not flung out of a swimming pool. So it's giving us the arrow of time. It's not at all clear it explains why teenagers' bedrooms are so messy or why countries fall apart, because the certainly true that the microstate part of the argument works just fine, but are they equally likely to move between them? Not so clear in that situation. The things that causes, say, a country or a room to move between microstates is not really a random process. But how about the universe as a whole? Now we've talked about temperature being uniform being a high entropy state, and temperature being ununiform being a low entropy state, so it tends to go from ununiform to uniform. But the universe has gone the other way. It was incredibly uniform in the microwave background era, and now the difference in temperature from one place to another is enormous. So isn't that violating things? And also talk about life forms like ourselves. We maintain a temperature that's different from around us. We are highly ordered, yet we probably came out of things in some sort of stagnant pool which was not highly ordered. So yes, we have this arrow of time, it all works nicely, kind of, but how can we explain things like that?
Sounds like maybe we need to bring in an expert.
Okay, so We have here at ANU Dr. Charlie Lineweaver, who is a expert who spent a lot of time thinking about this. So let's see what he has to say about this all.